Well, alright. We better start getting through this mammoth exercise. So you have a Noetherian ring A, and you want to prove that the ring of formal power series is also Noetherian. This is basically the Hilbert basis theorem, except that it's not. It's a little different. There's some things you do differently, but it's a very similar outline. And like the Hilbert basis theorem, there's a lot of stuff that you got to do. So anyways, what we're going to do is we're going to prove that every ideal of the formal power series ring is finitely generated. So let A be Noetherian, and suppose that we have an ideal in the ring of formal power series. We want to prove it's finitely generated. So suppose we have a non-zero formal power series, then we can write it as an infinite sum of coefficients in A times powers of x. We're going to find, these things aren't, so let I be the set of indices such that the corresponding coefficient is non-zero, and define the degree of f to be the minimum index. So the degree of f is the largest, it's the smallest integer such that the corresponding power of x has a non-zero coefficient. And then L of f is going to be whatever that coefficient is. So it's the coefficient of the lowest non-zero, or the coefficient of the lowest order term, which has non-zero coefficient. And because of the whole non-zeroness, I guess what you could do, if you wanted to, is you could define the L of f, the lowest order term, or the leading coefficient. You could define it for the zero polynomial to be, or the zero formal power series to be precisely zero, which I think in hindsight would be a little better, but I didn't do that here. So anyways, let's go. Let's keep moving. So, and because of that, we also have to manually insert 0 into this ideal here. But anyway, so for k greater than or equal to 0, let AK be the set of all leading order the set of all leading term coefficients for polynomials of degree equal to k. So, and of course, these are all polynomials that are in B. Now, I claim that each of these is an ideal in A, and because remember, these are the coefficients, and coefficients come from A. So these are elements of A. So for closure under addition, you take two elements in here. If A or B is 0, then that's easy, because then it's easy, because then the leading term of the sum is just, or if you add the two things, well, if one of them is 0, then the sum of these two things is just the one that's left over, and we already know that there's a polynomial in there that has that element of A as the leading coefficient, because that's what it means to be an element of A sub k. So anyways, suppose A and B are both non-zero polynomials. F and G, we know that there exist elements F and G and B whose degrees are equal to k. Well, I guess that's redundant, because that's what it means to be in degree. To be in A sub k. Oh, wait. No. We'll keep that. Well, so there's polynomials in B whose degrees are k. The leading coefficient of F is A, and the leading coefficient of G is B. The degree of these two things, the degree of the sum must also be k, because the degree doesn't change, or the degree of the sum can only increase. Ooh, well, I guess. And A plus B is not equal to 0. If A plus B is equal to 0, then obviously A plus B is going to be in there. Otherwise, so since if you take these two and add them together, then that leading term is not, the leading term coefficient is not going to become 0, so the degree is going to stay the same. And the leading coefficient is going to be a plus b, thus a plus b is in there, confirms closure under addition. Now if you have any constant if c is 0, then obviously this is 0, which is an a. If c is non-zero, then since b is a polynomial, multiplying it by, so we want to, b is an ideal in the formal power series, and just looking at the constant polynomial of constant c, well, that's an element of the formal power series, because then you just have a1 equal a2 equal all the way up, all the way up, and they're all equal to 0, and a0 is just equal to c. Okay, and this degree of c times f, well, c doesn't change the degree of f at all, so it's going to be precisely the degree of f, which is k. And what else? You have the leading coefficient of CF is, well, it's just going to be c times whatever the leading coefficient of f is, and that's just going to be CA, since A is the leading coefficient of f, using this same thing up here. So then the product is an AK, hence each AK is an ideal. Okay, now suppose you have an element A and AK. If it's 0, then it's an AK plus 1. If it's not 0, well, we know there's some f whose degree is k, and such that L of f equals A. That's what it means for A to be an AK. And then, if you just take this and multiply it by x, then this has leading coefficient A as well, and its degree is increased by 1. And therefore A is an AK plus 1 as well, so then we have an ascending chain here. And these are all ideals in A, and we know that A is Noetherian, so this ascending chain terminates by the ascending chain condition. So there is some k such that any k greater than or equal to k, you have AK equals AK. Alright. Now we know that every ideal in a Noetherian ring is finitely generated. Each AK is finitely generated. So we can write each AK as generated by AK1 through AKNK for some NK in here, and this NK of course depends on K, because each K is finitely generated, but we don't know how many finitely many generators there are. Choose N as, capital N is the max between N0 and capital N. Ooh. Should be NK. NK. These indices, that's one of the problems with this proof. It's not really the understanding what to do that's hard, it's writing it out, because there's so many indices that you need to keep track of. So this is N0 through N sub capital K. So we can write AK as AK1 through AK capital N for every K greater than or equal to 0. And so basically all I'm there is that I'm making sure that we can choose these n sub k's uniformly. Now certainly this will work when we go from n0 through n capital K, but why does it work for k greater than or equal to k plus 1, capital K plus 1? Note that this applies for such capital K because each such k is equal to a sub capital K, and thus is equal to this set. So because the chain here terminates, we can choose these for every single k, and it only goes up to n. Alright, so for each k between 0 and capital K and n between capital N, suppose f of kn is 0 if akn is 0. Okay, so that's basically what we really want is we want fkn in B to be the polynomial it's going to have degree k, and it satisfies the leading coefficient of this polynomial is going to be a sub kn. And the only reason I added in this stuff is because, well, by choosing capital N uniformly, some of these akn's might be 0. And that's fine. We just set the corresponding polynomial to be 0. Now, let's define A to be the set of, or the ideal in the formal power series ring generated by these polynomials, f, k, n, where k ranges from 0 to capital K and n ranges from 0 to capital N. I claim that this is precisely the ideal that we started with. Okay, so certainly every single A is contained in B, since each element of this generating set belongs to B, because we chose them as such. Now for the reverse inclusion, this is the one that takes work. So take an element F in this ideal B. We can write it as a power series, sum from 0 to infinity of ai x to the I. Now choose a k greater than or equal to 0. Note that if you have each ak is in the ideal a sub k, and so, right, it is in the ideal a sub k. Okay, here's what I think we need to do. I think we need to get rid of all that stuff. Okay, so let's take this f. Let f0 be the sum from I equals 1 to n of b0i f0i. Now, how are we choosing these b0i's? I've sort of crossed out the way I chose them before, because the way I chose them before is not quite right. Well, maybe it is. So let k equal 0. Then a0 is an element of a's. Well, I guess we have to, I guess what we really have to do is we need to start from the first non-zero coefficient. So where we should start is we should really start with the degree of f. So let k equal the degree of f. And we're going to find that as k. No. Okay, yeah. So that's k. Okay, so k is the degree of f. If k is the degree of f, then k gives us the first non-zero element here. Okay, well then, or the first non-zero leading coefficient. Okay, so if ak, so what do we know about ak? We know that there is an element f in our ideal B who has degree k and has leading coefficient ak. That's what it means for ak to be in the ideal ak. And the ideal ak is generated by ak1 through akn. And since it's in this ideal, there are coefficients bk1 through bkn such that we can write ak as the linear combination of the aki's times these bki's. Okay, so let's see here. So if we define f0 to be the sum of the boi foi's, or let's make this define f sub k to be the sum bk fk, then the coefficient of the term of order k of f0 is this sum, which is precisely a sub k. So then if you look at the difference between f and f0, then its degree is going to be at least k plus 1, because when you subtract these, the coefficients of the lowest order terms cancel out. And furthermore, this difference is in B, since fk is a linear combination of elements of B, because these fki's are in B. Well, the FKIs are in, yeah, the FKIs are in B. So it's a linear combination. So this is certainly in B, and F we chose from B, and so this difference is in B. So then we can write F minus Fk as the sum from I equals k plus 1 to infinity of ai prime x to the I. Okay, so what we've done is we've taken F and we've subtracted an element of B and achieved a new formal power series of strictly higher degree. And now we're going to do the same procedure, but instead of doing it to F, we're going to do it to F minus Fk, because we'll figure out what the degree of F minus Fk is, and then find a finite linear combination of elements of the of this A here, and we'll make it so that this so that we can cancel out with the highest order term. So we can find some F I'm going to call this K2, such that F minus K2, I'm going to call it K prime. K prime is an element of B of degree at least K plus, it's going to have degree at least K prime plus 1. Because we're saying that K prime is going to be the degree of F minus Fk. So degree of F minus Fk equals K prime. Okay? And so then we do the same procedure, and we get an element whose degree is greater than K prime. And then we continue this procedure to get F minus Fk all the way up through F K prime 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 prime. Okay, so here's what I'm going to do. To obtain an element, K prime 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 is greater than or equal to K plus 1, capital K plus 1. That's what I'm going to do. We're going to do this. I don't know these K's and these K primes and K prime primes. I don't know where these are. I don't know if we've surpassed capital K, because once we surpass capital K, we have to do things differently. So, if it turns out the degree of F is greater than or equal to capital K plus 1, then just skip everything here and just do what we will do in the next paragraph. Otherwise, you keep doing this initial procedure until we add enough primes to the top here to where this whatever integer we get will be greater than or equal to capital K plus 1. And this will happen eventually because there's only finitely many degrees which are less than or equal to capital K plus 1. And every time we add a prime here, we increase the degree by at least 1. Okay, so we're going to continue this process to contain an element, and I'm just going to keep this as F minus F0 dot 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 F sub K, capital K. I'm going to leave this as 0 through capital K. These really should be like lowercase k, lowercase k prime, all the way up through lowercase k to, like with a bunch of primes next to it. But at that point, I'm making too many edits to this. So let's just suppose that F0 through F capital K, well, to make this distinct from this capital K, let's call it capital K tilde. So F0 through F capital K tilde are elements of B which are chosen in such a way that when you take F and you subtract these polynomials, you get an element of, well, first of all, these F0 through Fk tilde, these are all linear combinations of these FKNs, like here. And once we subtract this, the remaining formal power series has degree at least capital K plus 1. And we know we can do that because of this procedure, which I've sort of completely butchered at this point, but whatever. Hopefully I made it clear enough that this process works. So anyways, we've now reduced to the case where we look at elements of B which have degree at least capital K plus 1. Okay? So now, for f capital K plus 1, we know that a sub k plus 1... Ugh, no. We have to do it again. We can't start with capital K plus 1. We're going to call this f capital K prime plus 1. Okay, so we don't know what the degree of this so this is going to be degree. So the degree of this difference is K, capital K prime. Why am I using capital K? What indices am I not using? L. Of degree L. And L is at least capital K plus 1. So now we're going to define FL. Since AL is contained in AL, and why is that? That's because it's the leading coefficient of this polynomial in B. But because L is greater than or equal to capital K plus 1, this ideal is equal to A sub capital K because the thing terminates. So then we can write A sub L as the sum of, let's see here, so BL1 sub K1 through BLN sub KN. And note here, these are capital Ks. And we are doing that because these capital KIs are in this ideal. So we're not choosing these AKNs. We're not choosing these from ideals beyond A sub K in the chain. And that's important. So since each capital KN, or such each F capital KN has degree K and lowest order coefficient AKN, we know that if we multiply this by x to the, and now we have to multiply by x to the power of L minus capital K, then this will have lowest order coefficient A sub capital KN, but its degree will be L. So if we let FL be the sum of these things, oh, no. We gotta multiply. We gotta multiply by x to the L minus K, x to the L minus K. Then the degree of f to the L is equal to K, capital K plus 1. And its lowest order term is A sub L. And so then if you take this and you subtract K tilde, and then you subtract F sub L, then this is an element of B of degree at least L plus 1. And now we continue this process inductively. Okay. So now, consider the sum from 0 to infinity of the FIs. So again, so we have F0 all the way up to F sub K tilde, then we have FL, then we're going to have, or here, what did we have? We had F0, we had FK, we had FK prime, then we went all the way up to FK prime, and then we had some unknown number of primes. Then we went up to FL, and then let's say from there we go up to FL B of degree L prime, which is at least L plus 1. So we'll have FL prime, and then we'll keep going, and eventually we'll get an indeterminate number of L primes, and then we'll just keep going from there. So we're going to relabel these. So this is going to be f0. We're going to go up to fk tilde. And this is going to be fk tilde plus 1, and so on and so forth. Okay, so this is going to be, now consider the sum from I equals 1 to 0. You know what, let's make these all tildes. Okay, so now consider the sum of these. And we can write the sum zero tilde. That's weird. No, this should be f0. Because k tilde and k tilde plus 1, those are just integers. Okay, so from I equals k tilde to infinity. So then if we're going from k tilde to infinity, then that's the same thing as okay, so first of all, we can look at the k tildes. Let's just, you know what we should really do here is we should just, if there's no, okay, here's what we're going to do. Here's what we are going to do. What we're going to do is we're going to take these fk's and we're going to just f0, f1, f2, and dot, dot, dot. And we're going to map these injectively into here. So all of these fi's that we're choosing here, they're only going to be corresponding with degrees that we need to cancel out in the polynomials. But in our proof, it's easier to deal with like all possible thingies here. All possible polynomials for like all indices from 0 onwards. So what we're going to do is if we have like some k or k prime, whatever integer that ends up being, we just can associate it with that particular integer. If we have an integer greater than or equal to 0, which isn't equal to some k prime or some l prime, then we're just going to consider all of the corresponding coefficients b to be 0. So let's do it that. I think that will be easier. Okay, so now let's look at the sum. Now we can write the sum. If we're going from capital K to infinity, we can take all the coefficients b's for here, and then for the next, so that this is going to give us the first order coefficient. And then for the second one, what we do is we multiply by x, because then it's going to correspond with the coefficient of degree capital N plus 1, and then capital N plus 2, blah, blah, blah. Again, all of these sums, if there's any index here that was not covered by one of these, then then the whole thing will be 0. Okay, so if we write the sum from k to infinity of fi's in this form, then we can rearrange these. Because look, here in every single one of these sums, we have an f capital K, comma 1. Because we go from f capital K, comma 1 to f capital K, comma capital N in every one of these terms. So we'll just group it by that. So here we'll take the sum from capital K to infinity of bk1 times x to the k minus k. So what we're doing is we're taking for each of these terms, we look at the f capital K, comma 1, and we take the corresponding b, then add on any corresponding powers of x if necessary. So we get this plus this. So now we have a finite sum here. And so then what is this? Well, this is just a linear combination of f capital K n's. Now so basically this thing here is going to be, So for the 1 here, so this is going to be C1, this is going to be C2, this is going to be C capital N. We correspond with whatever the second number here is. Here, and here. So this is the sum of C capital K comma N of Fk comma N from 1 to capital N. So here, where do these C capital K N's belong? These are just formal power series. They happen to have degree at least capital K, but that doesn't, well, sort of. Yeah, degree at least capital K, but that doesn't really matter. All that matters is that they're formal power series. So now A is an ideal, and each of these FKNs is an A because these are the part of the generating set. And so since it's an ideal, each CKN, FKN is an A as well because you're just multiplying by an element of the ring. And this holds for each N, and so this is just a sum of things in A, and so then this element is an A. So then, since this thing is equal to this is an A. And so then, well, what else can we do? If we take the sum from 0 to k minus 1 of Fk, well, we can similarly write this using the AKNs and the FKNs. Again, here we'll use the... Do we have to worry about the AKNs being 0? Yeah, let's just say that the AKN... Oh, well... Should these be B's? I think these should be B's. Yeah, B's and N's and B's and F's. B's and F's, yeah. Yeah. Okay, these should be B. These should be BKNs. Okay? And remember, so we're going to use the same sort of convention here, where the BKNs, we're going to take them to be 0 if the corresponding... so which ones are the degrees? The K's are the degrees, and the N's are the indices for the finitely generated ideals. So for each degree, if the corresponding K for the formal power series F, if the corresponding degree K has no associated coefficient, then we'll just take all of the BKNs to be 0, so that we don't get any contribution to that particular degree. Or no, you do have to, because it's because when you start with the lower degree, when you start with the lower degree, you have to cancel out those lower degrees, and those things can mess up what happens to the higher degrees. That's why we started low and went upwards. Because when we added in linear combinations of polynomials to get rid of the first lowest degree, then those polynomials that we added in could have taken coefficients of F whose corresponding degrees had 0 coefficients, and added polynomials in such a way that once you take the sum, you get a coefficient which is non-zero. And so yeah, you do have to be really careful with this. I clearly wasn't, and now this is a mess. But so the main point is when you're taking the sum from 0 to capital K minus 1 of Fk, the sum of all these polynomials, you don't run into any issues with finiteness. And you don't run into any issues with this possibly being an infinite sum, because all the sums here are finite. So anyways, this is an A. And this is a linear, so this is a linear combination. And so this is going to be an A because each FKN is an A, and so it's just a linear combination of things in A, and so it's an A. Therefore, this is infinite sum is an A. Okay, so now what? So, recall we chose Fi precisely so that the coefficient of the ith order term of this difference is 0. And this holds for every I greater than or equal to 0. So F minus this sum is 0. so f is equal to the sum. But we just proved that this sum is an A, and so f is an A. This holds for every f and b, so b is contained in A. Finally, and so we have A equals b. Now, we constructed A to be generated by a finite set, so it's finitely generated, so b is finitely generated. This holds for every ideal b in the ring of formal power series, and so every ideal in this ring of formal power series is finitely generated. Hence, this ring is also Noetherian, and we're done with the proof. Wow, that was a train wreck, and I am exhausted. Yeah. I don't know. I really don't like this proof now. At first I was like sort of meh about it, but now it's like... I feel like the idea here is really simple. It's just, in order to convey the idea, you need to use a lot of indices, and it becomes really complicated really easily. So it's just a matter of writing things and using symbols well. And I guess that is really important in math, but when it becomes more about the symbols than about the underlying ideas, then I don't like that sort of stuff in math. Anyways, here's a proof of this. Hopefully it was at least somewhat enlightening, but if not, then this should at least be an outline where if you want to understand what's going on here, you should be able to use this to help gain your understanding, whatever. Okay, I'm done here.